Okay, so today we're going to do something. We're going to start on basically basically a completely new set of material. Okay, so we've finished up integral calculus, right? That's it for integral calculus. And from here on in, we're going to be talking about sequences and series. Okay, sequences and series. The idea is, at least part of the idea is that you're going to take your functions and you're going to approximate your functions by infinite polynomials. Okay, so you know what a polynomial is, right? You have something like a naught plus a1x plus a2x squared plus an xn. Right? So you know what a polynomial is. But now you're going to take, instead of these polynomials that cut off at some point, you're going to have polynomials that go on an plus 1, xn plus 1, and go on forever. Okay. Now, this business of going on forever is the tricky part. Okay, because what does it mean to talk about how do you add numbers a sequence of numbers that goes on forever? It's not so simple as it might seem. You might think, oh, it's just like adding a finite number of numbers. Adding an infinite number of numbers is the same sort of thing, but actually it's quite different. Okay, so just to give you an example of how strange and how careful we have to be, let me show you this. Okay, so let's look at 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth. Okay, let's just look at that. Okay, and then let's look at half of it. Let's look at half. So this is some number, gamma. And let's look at 1/2 gamma. Okay, 1/2 gamma is just going to be like this, right? Minus a fourth plus a sixth minus an eighth plus a 10th minus a 12th plus a 14th minus a 16th, right? Nothing strange, right? And if I wanted to add those things together, okay, these are just finite numbers. You could give this to an elementary school student, and they would say, well, what I see is that, let's see. So I've got this. So I've got, let me do it. How am I going to do it? Plus the 6 minus 7. Okay, you can just cancel off some things, right? So maybe I'll take this half, I'm going to cancel off this half, right? Anyway, you just cancel and you add, and that's it, right? So it's easy. But okay, so let me write it again. Sorry. So suppose I have, again, 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth plus a ninth minus a 10th plus 11th minus a 12th, and I keep on going. Okay, I keep on going. And then I take a half of that. Okay, I get 1/2. I get minus a fourth plus a sixth minus an eighth plus a 10th minus a 12th plus a 14th. I'm running out of ink. Minus a 16th plus an 18th minus a 20th, etc., right? Plus minus. Okay. Okay. Now let's see. Okay. So now I'm going to add it together. Okay. Now I'm going to add this together. And I'm going to say, okay. Well, let's see. I've got this minus a fourth, and I've got this minus a fourth. Right, so those two become a half, and I can use that to get rid of this half, right? So these things cancel off, right? Right, okay. And then I've got, let's see, plus a fourth minus, I get a plus a third next. So got plus a third minus the fourth. Okay, so now I've got this minus an eighth, and I've this got this minus an eighth, right? So those two together become minus a fourth, right? So I'm gonna keep certain things. I'm gonna say I'm gonna keep this one. I'm gonna keep this half. I'm gonna keep this third. I'm gonna make a minus a fourth here, right? You see the minus a fourth? Everyone okay? So minus a fourth. There's plus a fifth, right? Now the 1/6 and the 1/6 cancel off, right? I have a minus a 12th and a minus a 12th here, so I get a minus a 6, right? Get minus a 6. I have a plus a 7th here, so I'm going to have to keep that plus a 7th. I have minus a 16th, and over here I've got minus a 16th, so I say minus an 8th, right? And the 10ths cancel off, right? And so on and so forth. Okay. Anyone disagree with what I'm doing? Is that okay? Does anyone have any trouble with that? Okay. So what do you see? What do you get? What do you get when you keep on going like this? What do you get when you go like this? You get the same thing that you started off with, right? You get the same thing you started off with. This number gamma. It's called gamma. It looks like alpha, right? This is alpha. This is gamma. Okay, right? Okay, so what does that say? That says that if I add gamma plus half gamma, right? 3/2 gamma is equal to gamma, right? Okay. Now I'm going to divide both sides by gamma, right? And I get 3/2 is equal to 1. In other words, 3 is equal to 2. Is gamma equal to 0? So that's the okay. So you were thinking maybe we divided by 0. Maybe that's what's going on here. Is gamma equal to 0? Let's take a look. Let's see. Gamma. Let's say this is 1. Okay. Gamma looks like you subtract half. Right. You subtract half, and then you add on a third. Right. Plus a third, and then you subtract off a fourth. Right. And then you add back on a fifth. You subtract off the sixth. You add back on a 7th, et cetera, et cetera. So it looks like gamma is not 0, right? Gamma is some number between, gamma is some number between 1/2 and 1, right? In fact, it's between if I sum up to here and I sum up to here, it's between those two numbers, right? So it's actually trapped between successive partial sums, right? So no, it's not 0. Gamma isn't 0. So gamma is not 0. So we can divide by it. We divide by it, and then we get 3 is equal to 2. Right? Or if I subtract 2 from it, I get 1 is equal to 0. Right? If we subtract 2 from both sides, if you look at it. Okay. So does anyone see what we did wrong here? The answer is we didn't do anything wrong, except it's not legal to play with infinite addition just like you do with finite addition. This business of just choosing and canceling off like this actually doesn't work. If you do things like this, then you end up with crazy statements like this. Okay. So the trouble is that infinite addition is not the same thing as finite addition. Okay. Infinite addition is not the same thing as finite addition, and you have to be much more careful when you're dealing with the sort of infinite sum than when you're dealing with a finite sum. Okay, so that's sort of the motivation for all of. So we're going to go through a lot of crazy things starting today, and this is why, because we have to be more careful about it. Okay. Okay. So it'll start off kind of simple. Start off kind of simple, but don't be fooled. It's actually, you have to be very careful when you're doing this. Okay. So 8.1, I think this is 8.1 sequences. So sequences. Okay. So sequences are something simple. It's just you have a bunch of numbers. You have a sequence of numbers, right? But the way we define it mathematically is like this. You say, well, any function from the natural numbers to the real numbers. So this is the natural numbers. Let's just say 1, 2, 3, etc. From the natural numbers to the real numbers is called a sequence. It's called a sequence. Okay. So you have some function f. It takes in a number and just gives you back something. So for example, if I say f of n is n squared, right, where n is in the natural numbers, then what I mean is that f of 1 is 1, f of 2 is 4, f of 3 is 9, forever, right? And so you get the sequence of numbers. You get the sequence of numbers 1, 4, 9, 16, 25, etc. Right? Okay. Or if I say f of n is -1 to the n, say, for n in the natural numbers, then that would give me, f of 1 is -1, f of 2 is 1, f of 3 is -1, and so on and so forth. Right? So this would be, -1, 1, -1, 1, -1, 1, going on forever. Okay? So these are examples of sequences. You know what a sequence is. You have some intuition of what a sequence is. Okay. So just a remark on notation. For notation, one usually uses A sub n, B sub n to denote elements of a sequence. Instead of f of n, g of n. See, instead of writing, f evaluated at n, you just write f sub n, f b sub n. So over here we would write, a sub n is n squared, b sub n is -1 to the n. Right? That's the more typical notation for sequences. Okay. So right. And one writes something like this, brackets a sub n, n from 1 to infinity, to signify the entire sequence. Okay. So use this bracket, right? Bracket a sub n. Sometimes people use the pointy bracket. I forget which one the book uses. I think the book uses this one. Okay, so just some notation, right? Nothing going on. More notation. Okay. you have two sequences, A sub n and B sub n are sequences. And let alpha be a real number. If we write alpha A sub n, this means this denotes the sequence alpha A sub n. Right? So you just multiply every element in the sequence. Right? So if I say alpha times n squared, right, then that's the sequence alpha, 4 alpha, 9 alpha, 16 alpha. So alpha is some number. So if I say like 3 n squared, right, then that's going to be 4 times 3. 4 times 3 squared, 4 times 3 cubed, etc., etc. Okay, it's just like function notation, right? When you write 5 sine x, right? You mean, sorry. Right. When you write something like 5 sine x, it's the same thing as 5 sine x. And it's just the same thing as function notation. I'll just erase this. Okay, so that's that, right? Also, as you might expect, if you talk about the sum of sequences, then continue.
It's 4 times 3 squared.
Oh, I'm sorry. What am I doing? What am I doing? So this would be, sorry, 3 times 4, 3 times 9, 3 times 16. Sorry. Thank you. If you write something like this, right, then it just means the sequence where everything is just summed, you know, all the things are summed together, right? So again, if I write n squared plus -1 to the n, right, then that's just going to be the sequence. When n equals 1, you get 1 plus -1, when n equals 2, you get 2 squared plus 1, when n equals 3, you get 3 squared minus 1, when n equals 4, you get 4 squared plus 1, etc., etc. Right? So you just do things, you know, element by element. Okay, and then, you know, as you might expect, again, if you're multiplying sequences, well, then you're just gonna multiply it element-wise. Okay. So this notation is pretty obvious, I think. So the real thing that we're interested in is limits of sequences. Limits of sequences. Right? How does the sequence behave as n goes to infinity? How does the sequence behave as n goes to infinity? So, for example, if you're thinking like -1 to the n, you know, as as n goes to infinity? What happens to it? The limit of -1 to the n over n as n goes to infinity. What happens to it? Right? The limit of as n goes to infinity of 1 plus 1 over n to the n as n goes to infinity. Right? What happens to these guys? The limit of 2 square roots of n over the square root of n plus 1 as n goes to infinity. What happens to it? See, we want to talk about limits, limits and infinity. Okay, just to get ourselves thinking, what do you think happens to this as n goes to infinity? What happens to this sequence? -1 to the n. As n goes to infinity, what does your sequence do? It'll bounce back between 1 and -1. It'll be -1, it'll be 1, be -1, 1, -1, 1, -1, 1. So it bounces back and forth, right? Okay, what about this one? -1 to the n over n. Okay, some people are saying 0. Yeah, 0 is right. But you see what happens, right? It's changing sign, right? It's first it's negative and then it's positive, it's negative and it's positive, it's negative and positive, right? But the size of it, right, if we look at the absolute value of it, if we look at the size of it is 1 over n, right? The size of it is 1 over n, as n goes to infinity, that becomes, closer and closer to 0, right? Even though it's bouncing back and forth, it's still, the size of it is still shrinking to 0, right? So it goes to 0. What about this one? Antini says 1. This is a tricky one. Right? If you take something bigger than 1 and you raise it to a power that goes to infinity, what happens? Suppose I have like 1 plus a tiny number. And I raise that to the nth power, and then I let that go to infinity. What happens? You get infinity, right? Suppose I take, however, 1 and raise it to any power, and I let n go to infinity. I let n go to infinity. Now, what? You get 1, right? So the answer, might be 1, or it might be infinity, right? Sort of depending on what happens here. Who knows the actual answer to this? What's the actual answer? There's sort of a tug of war that goes on. Does the exponent win? In which case you go to infinity, or does the fraction go faster? In which case you go to 1. Does anyone know the actual answer? The tug of war balances out at e. That's right. This actually turns out to be e, the number e. Okay, and we'll see that in a minute. Okay, what about this one here? 2 roots of n over root n plus 1. What do you think will happen to that as n goes to infinity? People are saying 2? Yeah, the answer is 2. Okay, and intuitively you say, well, look, this 1 isn't going to, when n becomes gigantic, this 1 is not going to make much difference. So it's basically 2 roots of n over root n, right? And that's 2. That's going to become closer and closer to 2. Okay, so you have some intuition about this, but just to be careful, to make this precise, we need to, we'll put some mathematical language on it. Okay, so, okay, so here's the definition. Okay, so let A sub n be a sequence of numbers. We say the limit of A sub n is L as n goes to infinity. If we can make A sub n as close to L as we want. If n is sufficiently large. Okay. So this is not actually this is not really a definition. It's more like an intuitive idea. Maybe intuitive definition. We can make A sub n as close to L as we want if n is sufficiently large. Okay, so let me try to make this a bit more concrete. Okay, so here's a sequence. 5 plus 1 over n. 5 plus 1 over n. Okay, what's the limit going to be as n goes to infinity? Oh, hold on. Looks like we've already. Here's a sequence, 5 plus 1 over n, right? It's going to be, 5, it's going to be 6, 5 and a half, 5 and a quarter, 5 and a third, etc. 5 and a third, 5 and a quarter, 5 and a fifth, etc. Right? Okay, what happens as n goes to infinity? You're going to get the number 5, of course, right? This is the limit of this is 5, right? And right, the picture is like this, right? Here's 5, and at time 1, you're at 6, right? At time 2, you're at 5 and a quarter, 5 and a half, right? At time 3, you're at 5 and a third. At time 4, you're at 5 and a fourth, right? And you're getting closer and closer. You're getting closer and closer to the number 5, right? Right? And so the way we're expressing this is that we can make the number as close to L as we want if n is sufficiently large. Okay. So if I said, where past what time, let's think of this as time. Past what time is A sub n always within 1/10 of 5? Okay, so here's the question. Past what time is A sub n always within 1/10 of 5? Okay, don't blurt out the answer. Think for 10 seconds. Okay, what's the answer? The answer is, well, 10, right? Certainly, right? At 10, we are at 5 and 1/10, right? And as long as we're past 10, all the numbers we get are within 1/10 of 5, right? All the numbers we get are within 1/10 of 5. Okay, suppose I say, past what time is a sub n always within 100th of 5? What's the answer? Turn to somebody nearby and tell them what the answer is. Xu Chen Chen.
Yes.
What's the answer?
Almost
100, yeah, right? Because, right, if we come out to time 100, what's the value? The value is going to be 5 plus 100, right? It's going to be 5 plus 100, and past that time, all the values are even closer to 5, right? Past that time, all the values are even closer to 5. So, right, so as long here, as long as n exceeds 100, then a sub n minus 5 is less than 100. Right? As long as n is bigger than 100, then a sub n minus 5 is smaller than 100. Right? And you could see that more mathematically. And so this is sort of like, you just see it, it's obvious, but you could, if you want to see it mathematically, you say, well, right, so mathematically, let's look at a sub n minus 5. A sub n minus 5 is 5 plus 1 over n minus 5, right? Which is just the absolute value of 1 over n. So if n is bigger than 100, 1 over n is smaller than 100. Right? So you see that. So a sub n minus 5 is smaller than 100 for n bigger than 100. Okay. So let's do another example. Let's do another example. Let's say a sub n is 5 plus 1 over n squared. Okay? 5 plus 1 over n squared, and the question is, past what n is a sub n within always within, say, 1/100th of 5, right? The limit is again going to be 5. Let's see if we can do this. You know, past what n is a sub n always within 100 of 5. Okay, so take one minute. Okay, talk to somebody nearby, please. Just for a minute, please call. Yeah. Okay, so what's the answer? What's the answer? Of course. What's the answer? 10. 10, right? The answer is 10, right?